Now, when it comes to stress, I'm gonna create a couple more stresses. So I'm just gonna drag the equivalent stress back onto solution to create that really quickly. And I want time step 2 here, and I want time step 1. And it's not real time, it's just more of a, this is what we put in that particular step. Okay, so equivalent stress, bolt preload, little to no stress in the nozzle as expected, and then the stress in the bolt is 60 KSI. Now, the preload that I obtained, this makes sense. If I take the preload and I divide it by the area, that would be equal to the 60 to 61 KSI. That's expected.
And we will show students that hand calc in,
sure.
in verification. So that'll be part of the verification.
Yes, exactly. And the quickie way of doing this is that if I were to click on static structural, let me click on this face. And then if I click on that face, if I look at the bottom of the screen, that's 0.038 inches squared. And then I have my force right here. The bolt pretension. So my bolt pretension is 2320. The actual full bolt pretension is 4640. I divide by 2 because that's a symmetry model. But to get the stresses, I would take 2320, divide it by that cross-sectional area right here, and then I would obtain my 60 or so KSI. So that's a check mark right there. And then when it comes to the next equivalent stress, I'm gonna also put a probe right here. The stresses are a little bit higher now that I've added pressure stresses. I'm gonna jump to the final time step where things are moving around, and then stresses are again slightly higher. We're talking about 10% higher. I'm not really concerned as a stress analyst because it's designed for that. What's interesting to me as well is what are the stresses in the nozzle? So what I'm going to do is I'm going to click on I'm going to click on the nozzle. I'm going to hide all the other bodies. I'm going to go back to equivalent stress, and I'm going to right click on this graph right here and do adjust to visible. It's showing some of the contact stresses or bearing stresses between the flange there. That's interesting. However, I'm also interested in what is the nozzle seeing. So I'm going to scale this bar until it becomes dramatic. So here, that's drama. and then I'm going to sample some of the stresses. Stresses are high here because it's in bending. That's of interest. Primarily, I really want to know what's happening because of hoop stress, which is equal to pressure times radius over thickness. So great. Before this talk, I calculated this ahead of time. The pressure in this region is 12.17 psi, and then I multiply that times the radius. And if I did not want to have to go back to the geometry, by the way, I could just click on this, and it shows me that the radius is 69 inches because everything's centered. It's a type of cylindrical coordinate system. So and then I can divide it by the thickness. And hey, the thickness is a ½ inch. So that's the way I designed that. And that's
PR over T, right?
Yes, exactly.
Yeah. And that's a hand calc that we did in the pre-analysis.
When it comes to the thermal environment, I actually don't, the stresses don't really change. It's just that everything grows. The molecules are moving further apart based off of the behavior of the atoms and molecules. However, the stresses don't change because of that. So the stresses look good to me because I'm comparing the stresses to the capability of the material. The capability of the material for this temperature is between 15 and 20,000 psi. So a stress in this region of, say, 7,000 psi is well within range. We have some compressive stresses here, which is fine. We could take more look at bearing or contact stresses here and would actually see more capability. I'm not too worried about that stress concentration that we saw over there. And then when it comes to the bolt, the bolt capability here is based off of Google, is 160,000 psi, and we're only operating at, say, 70-ish. We're operating below 70,000 psi, indicating we're actually doing pretty good.
That's great. Thank you.